Okay, maybe it's time to start.
Okay,
It's
I'm
my
ready.
great pleasure to present our today's speaker, Professor Armen Sergeev, and the talk would be mathematical problems in the theory of topological insulators. So please go ahead. Thank you.
Thank you. First of all, I want to thank the organizers of the seminar, Alexey Karapetyants and Vladislav Kravchenko, for the invitation to give a talk at this seminar. So the topic, you see the topic, topic is related to topological insulators. And let me start with some introductory words. So as I said, the talk is devoted to one of the most interesting and actively developing themes in the condensed matter physics, namely the theory of topological insulators. We have chosen this particular topic since, apart from its importance for theoretical physics, uh, I was attracted by the numerous connections of this theory with various directions in modern mathematics, including topology and homotopy theory, Clifford algebras and K-theory, non-commutative geometry, and C-star algebras. The role of topology in the theory of condensed matter first became clear in the study of the quantum Hall effect, starting from the papers by Laughlin and Towles with co-authors. The topological insulators are characterized by the wide energy gap, which is stable under small deformations. And this motivates the application of topological methods. A key point in the study of topological objects in the solid state physics is played by the symmetry groups. There are three basic types of symmetries, namely the time reversion symmetry, preservation of the number of particles, or in other words, charge symmetry, and pH symmetry, which means particle hole symmetry. The description of this and other symmetries arising in solid state physics goes back to Alexey Kitaev, who proposed the classification of topological insulators based on this study. In our talk, we pay main attention to the topological insulators invariant under time reversion symmetry. So that was some short summary of my talk. And now I try to explain all this in detail. So let me start with recalling what is Bloch theory. Classical Bloch theory describes the properties of solid bodies which have the crystal lattice, called in this theory Bravais lattice. From mathematical point of view, this lattice is a discrete abelian group gamma in the space Rd, with d equals 3, isomorphic to ZD, and acting on Rd by translations T gamma, generated by vectors gamma from this group gamma. So we have a group which acts, a discrete group acts by translations. The behavior of free electrons in a solid body is determined by the one particle Schrodinger equation. This is equation of this type. This, of course, is written for eigenvalues for this operator. And V is a delta is the usual Laplacian, and V is a periodic potential. Invariant, which means that it is invariant under the action of gamma. Such operator H, Schrodinger operator, of course, commutes with all operators T gamma of translations by gammas. We also consider the dual lattice gamma prime in the momentum space Rd prime, which is defined in the following way. This gamma prime consists of the vectors k from Rd prime, such that the scalar product between k and gamma is integer up to this coefficient for all gamma from gamma. The fundamental domain, or in other words, a unit cell, which I denote by m gamma prime, of the lattice gamma prime, is called the Brillouin zone BRD, which is the torus. And this Brillouin zone plays an important role in what I shall speak later. Okay, the functions invariant under gamma may be considered as functions on the torus, as I said, which is the quotient of Rd by gamma. We denote by H sub 0 the Hilbert space. This is just L2 space on this torus with respect to the standard Lebesgue measure dx on Rd. The exponential, which I denote by Ek, this is exponential of I k scalar product with x, belongs to H0 if k belongs to this dual lattice. Moreover, such functions form an orthonormal basis in H sub 0. We consider also the smooth functions of the following form. This is e to the power I chi x, which I just introduced, times phi of x, where x is Rd. Where vector k, this vector k standing here, belongs to the Brillouin zone BRD, in other words, to the torus. And the function phi standing here, which is assumed to be a smooth function on the torus. So this function having this form, as written here, is called the Bloch function. And the vector k standing here is called the quasi-momentum. And the space of Bloch functions with quasi-momentum k is denoted by L sub k. These Bloch functions play a very important role in all this theory. Let's consider how the Schrodinger operator acts on such functions. It acts by the following formula. If we apply h to this Bloch function psi of x, then what we will get, this is up to this factor, e to the power chi x, is some operator h sub k phi of x. So this formula is very easy to check. And the operator hk standing here is called effective or Bloch Hamiltonian. And this is just a very simple operator of this form. What is important? That this operator h sub k maps the space C infinity on the torus to itself. It follows that the original Schrodinger operator h, which is the same as h sub 0, maps the space of Bloch functions with quasi-momentum k to itself. If we denote by ik the operator of multiplication by this fundamental function, this exponential, then the above formula, I mean the formula, this formula written here, may be rewritten in the following form, that h, this is operator ik, operator of multiplication, is equal to hk. So h is conjugate to hk with the help of this ik. In other words, if we consider h on the space of Bloch functions with quasi-momentum k, this is the same as a hk on the space L0 and this conjugated by ik. So in this way, the study of the operator h on Lk, which is our main goal, is reduced to the study of this operator hk, this Bloch operator hk, on the subspace L0. This is just L2 subspace. Denote by hk the closure of operator hk restricted to L0 in the space H0. Then we will get the operator hk with the definition domain which coincides with the following subspace. It consists of function phi of x, which are written in this Fourier as this Fourier series, such that the following series is finite. This subspace, this subspace, in fact, may be identified with the usual Sobolev space H2 on the torus. If we provide this H2 with the inner product given precisely by this series, like here, and also multiplied to make it orthonormal, this well, okay, to make this I will not speak, but of course we can prepare functions of this form as an orthonormal basis. And to make it orthonormal, we usually multiply by V gamma, where V gamma is the volume of fundamental domain M gamma of the lattice gamma. So this operator is very good. The spectrum of operator H of K is discrete, and its eigenfunctions phi m of K, which are solutions of this eigenvalue problem, form a complete orthogonal system in the Hilbert space H sub 0. Now, what is the physical interpretation of this? The collection of energy levels which corresponds to the eigenvalues Em of K with fixed M, so depending only on K, is called the energy zone. So the energy zone is the zone of this energy levels with this fixed M. So this eigenfunctions Em of K, in fact, determine the zonal structure of the solid body. And this is the main problem of this Bloch theory, to study this zonal structure. Now, what is the ground state of the system with n levels? So the state with the lowest energy. It has the following structure. There is a number P of completely occupied one electron levels with energy not exceeding some quantity EF, which is called the Fermi energy. Above it, there are n minus P empty or non-occupied levels. The interval between the highest occupied level and the lowest empty level is called the energy gap or forbidden zone. And the solid bodies with wide energy gap, which is stable under small deformations, are called the insulators. So we are going to study the insulators. The block functions, corresponding to this basis phi mk of this eigenvalue functions, are the eigenfunctions of the original Schrodinger operator H. Now consider again the space Lk of the, I recall that this is the space of block functions with quasi-momentum k, and denote by hk the compression of the space with respect to the norm determined by this isomorphism between L sub 0 and L sub k. So that this ik, I recall that that was multiplication by exponential, extends to the isometry. So these are isometric. This H sub 0 and H sub k are isometric with respect to this ik. Now, one of the main constructions is the vector bundle pi over the Brillouin zone. I recall that Brillouin zone was this our torus. And I denote this vector bundle by Gothic H. It has the fiber HK over the point K, and denote by H calligraphic, or this is the same as L2 of H, the Hilbert space of square integrable sections of this bundle with respect to inner product S1, S2, which is just the integration of the inner products on the fibers, HK. This space H, in fact, is the direct integral of Hilbert spaces HK over the Brillouin zone with respect to measure decay. But I will not explain what does it mean direct integral, just for those who knows what is that. Okay, now I have recalled the basics of the Bloch theory. Now our main goal is somehow to describe the topology of these insulators. How to describe them? Okay, I recall that H of K was the Bloch Hamiltonian, describing the zonal insulator with forbidden zone on the level of Fermi energy EF. We can, of course, diagonalize it by unitary conjugation. We can always find unitary function of K, such that we get in the right-hand side with just this diagonal matrix with eigenvalues E1 and En of K. Suppose now that the first M levels, which are lying above the Fermi energy, are empty. And the occupied levels correspond to the levels with energy less than Fermi energy. There exists Now, one of the important remark. There exists the adiabatic deformation of this Hamiltonian, of our Hamiltonian, which means that this is just continuous deformation of our Hamiltonian in the class of considered Hamiltonians, which does not affect the forbidden zone. Then we can find such adiabatic deformation of our Hamiltonian to a Hamiltonian with only two energy values, equal for all occupied levels -1, and for all free levels 2 +1. In fact, this deformation may be given by an explicit formula using the spectral decomposition theorem, but I will not stop here. In other words, if we have this, what does it mean that we have such deformation? It means that there exists a matrix U of k such that conjugation of this h of k with respect to this u is just diagonal matrix, which is just block diagonal, where the first block is just one unit matrix of m by m, and the other block is minus identity matrix of this dimension. Note that the matrix U of k in this equation, now we are interested in this equation, and we want to use it to define the topological invariance. And I note that, first of all, that the matrix U of k in this equation is defined only up to transformations of this form. So we can multiply it by diagonal matrix consisting of unitary matrix of such size. Hence, the metric U of k, which yield a solution of this above equation, determines a map from the Brillouin zone, which is just a torus, to the Grassmannian. Grassmannian is just a quotient of unitary group U of n by the product of U of m and U n minus m. It follows from this remark. So we have arrived at the problem of description of homotopic classes of maps from the torus TD to Grassmann manifolds. In fact, this general problem of description of these homotopic equivalence classes of continuous maps from the torus to topological spaces X was studied by Fox. That was one of the initiator of knot theory. The structure of this space, according to Fox, is determined by the collection of the following maps, which I denote by omega R I, which are the maps from the usual homotopic group of dimension R to this space, where R is strictly less, not strictly less, not greater than D. What are these maps? These maps are parameterized by the ordered subsets I, which is I1, IR, in the set of indices from 1 to D. So, in fact, we can, using this result of Fox, we can reduce the study of such groups to the study of the homotopy, usual homotopy groups. Accordingly, the elements of this space TD may be parameterized by the collection of the different elements of different homotopy groups. In fact, they can be parameterized by D elements from the group P1, D by minus 1 divided by 2 elements from pi 2, and so on. This is binomial coefficients, D sub j, elements from pi j, and so on. So everything is reduced, in fact, to the study of the homotopy, usual homotopy groups. Okay, return now to the above problem of the description of these homotopy classes, where X is the Grassmann manifold. Applying the Fox construction to the Grassmannian, which we are interested in, we get for D equals 1. I just give 2 examples which are most interesting from physical point of view. For D equals 1, this group is the same as pi 1, as I said before, and pi 1 of Grassmannian is equal to 0. if n is sufficiently big, and we shall always assume this. For d equals 2, the homotopy classes of the maps from the two torus to Grassmannian are characterized by the unique invariant since pi2 of Grassmannian is z. And for d equals 3, the homotopy classes of the maps from 3 torus to Grassmannian are classified by 3 elements from the group pi2 of Grassmannian, which is z. Since, as I already said, pi1 and pi3 of Grassmannian are equals to 0. So how to describe this in more natural way? In fact, non-trivial classes and dimensions d equals 2 and 3, most interesting from physical point of view, are described in the following way. The space, note that the space of these homotopy classes of maps from the torus to Grassmannian may be considered as the classifying space for the bundles over TD. In dimension d equals 2, there is only one non-trivial bundle over T2, which is analogous to the Hopf bundle over S2. This is bundle S3 over S2, the Hopf bundle. From the physical point of view, this case is very important, and it corresponds to the quantum spin Hall insulator, one of the most well-known insulators, non-trivial topological insulators. In dimension d equals 3, there are 3 bundles over T3, which are the pullbacks of the Hopf bundle with respect to 3 different projections from T3 to T2. So these are these 3 different bundles. Okay, I have described the general idea how one can describe the topological invariance. And now I switch to the time reversion symmetry. As I said, this is most important for us. This symmetry is given by the so-called T transform, that is by the operator T, which satisfies this condition, T squared is minus identity, and is anti-unitary. Anti-unitary means in the sense that T phi, T psi is equal to psi phi. So we have interchanged phi and psi by the places. It's contrary to the unitary operator. It implies in particular, this is very important because it implies in particular that the state phi and this T partner, T phi, are orthogonal to each other. That means that phi and T phi orthogonal product is equal to 0. Indeed, if we consider this inner product, T phi and phi, we can write this I as T squared minus, and then we use this anti-unitary relation. We just change the places, and what we get is the following. So we have here T phi phi and here minus T phi phi. So it means that this scalar product is 0. Why it is so important? Because it seems it means that these states have the same energy, first of all, and it means that any energy eigenstate is double degenerated. This is very important for the study of this T-symmetric insulators. This effect is well known in physics, and it's called Chromos degenerations. So every eigenstate, energy eigenstate, is double degenerated. Now, we want to describe this T-symmetric insulators in mathematical terms. What does it mean? The topological insulators with the time reversal symmetry are described mathematically in terms of involutive spaces. From this moment, our exposition becomes more abstract, and accordingly, we change some notations. In particular, the momentum space of a topological insulator will be denoted further on by X, with its points denoted by X small. We shall also suppose that X is a connected compact topological space. Again, I know that if the coordinate space is determined by the lattice in RD, as in the first part of my talk, then its momentum space is the torus. This brilliant zone is just the torus. But here we don't suppose that here is X is more or less general topological space. Then what does it involutive space? Involutive space, X tau, is a topological space X provided with the involution. That is a homeomorphism tau from x to x with the square equal to identity. So this is in volatility space, and we want to describe topological insulators, symmetric under time reversion in terms of different involutive spaces. How to do that? First of all, we shall call this involutive space is also called R space. And let me give one example of this R space. This is the space RPQ, which is RQ plus IRP. And coordinates are denoted as y and x. So y is taken from RQ and x is taken from RP. The involution on this space is given by the map tau, which sends yx to the pair y minus x. In fact, this T-symmetry in the general involutive space, x, is usually given by the change of signs of local coordinates. So this is just a general idea. For example, if the sphere as SD is realized as a unit sphere in the space Rd plus 1 with coordinate x sub 0, x sub d, satisfying the relation x sub 0 squared plus x1 squared plus xd squared equals to 1, then it is natural to define the T-symmetry operator on it by the following map. We just leave x sub 0 as it is, and we change the signs of x1 xd to minus x1 minus xd. For the torus, if we consider the torus, given by with coordinates e to the power I theta 1, e to the power I theta d, then the T-symmetry is given just by changing the all signs of these thetas. Very important for us, the very important notion is the set of fixed point of involution tau. This is just the set which I denote by x tau, where tau of x is equal to x. That's a standard notion. But we suppose that it consists of a finite number of points. This is very important. In the above example of the sphere SD, the involution tau has just two fixed points, namely plus minus 1, 0, 0. While the involution on the torus tau d has 2 in the power d fixed points, which are given by the following collections of epsilon 1, epsilon d, where each epsilon is equal to plus or minus 1. Now I return to the Hilbert bundle, which I already introduced before, the Hilbert bundle of topological insulator. Recall that we denote by pi, this Gothic h to x, the Hilbert bundle of the topological insulator over the momentum space x, which was before it was just Brillouin zone. The fiber of this bundle at the point x small is the Hilbert space hk, before I denoted by hx, before I denoted by hk. And we denote by h, as before, the Hilbert space of its square integrable sections. These sections are identified with the physical states with eigenfunctions E of x. The time reversion transform on the space H is given by the operator theta. So we are now working here in this H. So this is the space of sections of this bundle. So the time reversion transform on the space H is given by the operator theta, which is an anti-unitary operator, satisfying the conditions that square of theta is equal to minus 1 and Hermitian conjugate of theta equal to minus theta. Now the definition. We shall call by Q bundle, which I denote by E rho, over the involutive space x tau, a complex vector bundle E of x, provided with the, not with involution, but with anti-involution rho, which is compatible with tau. The anti-involution rho is given by the antilinear bundle isomorphism rho from E to E, such that its square equal to minus identity. And the compatibility condition of rho and involution tau means that pi composition with rho is the same as T composition with P. Simply speaking, we have here anti-involution on E, and we have here involution pi, and this rho projects to pi on x, to tau on x, sorry, to tau on x. At fixed points of our involution, the map rho x from ex to ex. It is an antilinear map with rho squared x equal minus identity, as I already said here. So rho x defines a quaternionic structure, actional quaternion on this fiber. And in fact, this is the reason why we call this Q bundle. So we have, these are kind of quaternionic bundles. If we replace in this definition the anti-involution rho by the involution sigma, such that sigma squared is identity, then we obtain the definition of the R bundle, E sigma over X tau. So the Hilbert, the Hilbert bundle, if we return to our Hilbert bundle, but now provided with time reversion operator theta, it becomes the Q bundle from H theta to X tau. In other words, the involution tau on our original involutive space is pulled up to the anti-involution on the Hilbert bundle. So in fact, this is the way how this theory of topological insulators is related to K theory. In the K theory, we should consider all these bundles, Q bundles or R bundles, and consider them up to the stable equivalence. And then we got the K functor, which is called here KQ functor or KR bundle. But to save the time, I shall not speak about it now, but this is also a very interesting topic. Now let's return to our Hamiltonian H of x, which is invariant under time reversion. It should satisfy the following condition. So you see, if we conjugate with this theta, then we get the H, but in another point, tau of x. Hence, if phi is an eigenstate of H, that is, we have the following condition. Then theta phi is an eigenstate of theta H, theta star, with the same energy E. This is the same energy. So the energy is the same. We just move the point X. So it is written here. It is written here. In other words, the states phi and theta phi belong to the same zone with the energy E. So every zone under the T symmetry is double degenerated, and phi and theta phi form the Kramers pair. So as I said, this is very important, this Kramers degeneration, and all Hamiltonians invariant under time reversion, they have this degeneration. In this case, the ranks of our Hilbert bundle, which I assume to be finite, is even. That is equal to 2n, where n is a natural number. If T is the only symmetry of our H, that is, every zone is precisely doubly degenerated, then H is represented as the direct sum of subbundles Hi, which are subbundles of rank 2, with a space of sections generated by the Kramers sections phi I and theta phi I. So this is the structure of this Hilbert bundle of our insulator. Now I denote by Wi the transition function of the bundle Hi. So this is the map from X to U2, to this unitary group 2. The T transform on H changes Wi to Wi composed with the complex conjugation. In terms of local coordinates xv on Hi, the operator theta acts by the following formula. If we use the relation that theta squared is minus identity, we arrive at the following equality. That is, if we transpose WE, this matrix transpose, then we get minus W of x. What is important, that if we consider this relation at fixed points, so that tau of x is equal to x, the matrix W of x is Q-symmetric. This is very important for the future. In particular, when here is an example. If x is just S3, written in this standard form as a sphere in C2, then the T symmetry is given by this formula. just changing the beta and conjugate alpha. Its fixed points are just two fixed points, and the transition function from S3 to U2 is given by this simple formula. So this is our transition function. And now I come to a very important notion in solid-state physics, namely Majorana modes. And I introduce the first analytical Z2 index. Let H of X be a Bloch Hamiltonian on the momentum space X. As I said, it is T-invariant if we have the following equation. For topological insulators, the Hamiltonian H of X at a fixed point X sub 0 may be approximated by the Dirac operator with a quadratic error term. This fact is very well known for physicists, and of course it can be also proved mathematically, but let me skip this at the moment. And consider the simplest case when the Hilbert bundle, this H of Rx, has just rank 2, and the space of sections is generated by Chromos sections phi and theta phi. This pair of sections having the same energy may be considered as a quasi-particle, which is composed of two states, phi and theta phi. Its effective Hamiltonian has the following form, or Bloch Hamiltonian has the following form, this matrix form. This Hamiltonian H tilde is T-invariant, where T is I just defined earlier, and the equation for the eigenvector phi of H with eigenvalue E takes, in terms of this H tilde, the following matrix form. Suppose that on the space of sections of the bundle H, we have a real structure I, which is an operator, which is I squared is identity, and I star is equal to I. Then a state psi is called the Majorana state with respect to this real structure I, if it satisfies the reality condition, I psi equals to psi. Using the time reversion operator theta, we can construct a real structure on H by, I should be H tilde here, by setting the following form. It acts on the Kramers pair phi by this formula. That is very easy to compute. So this phi, which is this quasi-particle composed of phi and theta phi, is the Majorana state with respect to the real structure I. So Majorana states, it has a special states which has a real in this sense. They are fixed by this real structure I. Now, the next definition. This is localization of our definition of Majorana state. The Majorana zero mode is the Majorana state phi sub 0, which composed of these two states, which is defined in a small neighborhood of a fixed point X sub 0, such that phi and theta phi are equals to 0 at this point, and such that this phi sub 0 changed the sign at this point. So this is localized version of Majorana state, which I just defined. Suppose now that the operator H, and hence also H tilde, is Fredholm. Then the operator H of X near the fixed point X sub 0 is the sum of the Dirac operator and quadratic error term, as I said before. And this error term does not affect the homotopy class. So the index of the topological insulator may be determined by the index of Dirac operators at all fixed points. In a neighborhood of a fixed point X sub 0, the operator H tilde may be approximated by the Dirac operator, which corresponds in the matrix form to the operator of this type. And I denote, so here is Dirac operator minus Dirac, and here what I call matrix Dirac. So the operator H tilde near the fixed point X sub 0 is represented as the sum of the skew-symmetric operator D, which I just introduced, and the quadratic error term, which, as I said, has no impact on the index of operator H tilde at this point. For real skew-symmetric elliptic operators P, Atiyah and Zinger define their analytical Z2 index in the following way. This is a dimension of the kernel of this operator modulus 2. So this is the index of operator P in this point A. So it is natural to define that Z2 invariant of a topological insulator, as I said, as the sum of all these indices, sum over all fixed points. So it is the sum over all fixed points of dimensions of this kernel of this operator, H tilde modulus 2. In physical terms, the Z2 invariant, which I just introduced, is equal to the sum of the parities of the numbers of Majorana zero modes taken over all fixed points X. So this is the first topological index, which is very important, and I call it analytical Z2 index. Now, there is another notion, which is a topological Z2 index. It is defined in the following way. Consider the construction of the topological Z2 index for the three-dimensional involutive space X tau. This is important that it's three-dimensional. Generalization to other dimensions is still a problem. Suppose that the Hilbert bundle P is a gain of rank 2 and the gauge group coincides with U2. Then the anti-involution theta on the Hilbert bundle is compatible with the natural involution theta on the group U2, which is given by the standard formula. This is the standard involution of the unitary group. And this is compatible in the usual sense here, where W is the transition functions. In other words, W, the transition function, defines an equivariant map from X tau to the group U2 provided with this involution theta. Now I recall that there is in topology, there is well-known notion of odd Chern character of a smooth map G from X to U of n. In fact, to this unitary group of dimension n. It is defined by the following formula. It is the sum of all odd dimensional Chern characters, Chern numbers. And if we want to write down it, then these Chern numbers are given by the following. This is the trace of the matrix G minus Dj in the power 2k plus 1, and we take the trace of this. If we use this formula from topology in our three-dimensional case, we can introduce the topological index of this G in the following way. This is just integral over the space X of, there is only one here, this three-dimensional Chern number. Or we can rewrite it like that using this formula. This number is also called the rotation number of this map G. Due to T-symmetry, the topological index taken of the transition function W. So instead of G, we now take transition functions from X to U2. This topological index is defined modulo Z2, in fact. And the assertion that this topological Z2 index for three-dimensional topological insulators coincides with the analytical Z2 index, that is, that mu is equal to index of W, may be considered as an analog of Atiyah-Zinger index theorem in our situation. So due to this Atiyah-Zinger index theorem, these two definitions coincide. Another definition of topological Z2 index was proposed by Kane and Meal. This invariant, which we call the Km invariant, is defined by the following formula. We take the product over all fixed points of this in the nominator. We take the Pfaffian of W of X, and in the denominator we take the square root of determinant of the same matrix W at X. As I pointed out before, this transition function W of X at fixed points X, and here we consider only fixed points, is a skew-symmetric matrix. So its Pfaffian, denoted by Pfaffian of W at X, is correctly defined. As we shall prove, the introduced Km invariant coincides with the product of signs of Pfaffians over all fixed points. How to prove that? I'm sorry, I have a question to organizers. Shall I recall the definition of Pfaffian, or I can assume that it is known?
I guess it's up to you.
Okay, let me then recall the definition. Suppose that we have A, which is a skew-symmetric matrix of dimension 2n times 2n. We can associate with this matrix the bivector of this form, where this Aij is this matrix. And EI is the standard orthonormal basis in R2n. Then the Pfaffian of the matrix is defined by the following inequality. We take the nth power of this bivector, and in the right-hand side, we take the standard bivector in our space R2n, and then this factor, which we have here, is precisely Pfaffian. This Pfaffian has the following properties. Of course, if we take the square of this Pfaffian, this will be determined. If we multiply A by lambda, then this is the same as this relation. If we consider the conjugation of A with some matrix B, this will be the same as like that. And if we take the transpose matrix, this is the same like that. It is well known that the square matrix, just the usual square matrix, satisfies the following identity. If we take the logarithm of the determinant, this is the same as the trace of the logarithm. In the case when this matrix A is skew-symmetric, this identity transforms in the following form, has the following form. Again, we have here trace of logarithm, but in the left-hand side, we have 2 multiplied by logarithm of Pfaffian. We can use all these relations to formulate the following relation between Km invariant and the topological Z2 index. It is established using the following formula, which is due to Kaufman with co-authors. So it is the main formula. So the sum of these logarithms of Pfaffians, it should be here 2, as you know. So we here 1 over 2. And this is the same as the topological index of the transition function W. If we exponentiate this equality, we obtain the equation relating the product of Pfaffians with the topological Z2 index. So we take here the product of Pfaffians. And here we have exponential of this, what is standing here. And this is the same as -1 in the power of topological index. If we set the determinant at fixed point x equal to 1, we can always do this. We get that the Pfaffian of W at x at such points is equal either to 1 or to -1. So the product in the left-hand side, in this left-hand side, this product of Pfaffians is equal to this Km invariant of x. And it will not change if we replace the Pfaffian by their signs. Hence, we arrive at the following formula, that Km invariant of x is the product of the signs of Pfaffians over fixed points x. And this is the same as -1 in the power of topological index. So this is the relation between topological Z2 index and Km invariant. So here it's all that I wanted to speak about. Of course, I will be glad to answer all questions. But let me say that this invention of topology in this condensed matter physics was like it's like a breakthrough in this theory, because the physicists understood that if the topological indices are different for different insulators, these insulators physically are absolutely different. For example, as I said, this quantum Hall, spin quantum Hall insulator, which is one of the most well-known insulators, is quite different from the usual insulator. And so this was of course, this fact was very unexpected for physicists, and they were very happy with that. Thank you very much.
Thank you very much for your very nice talk. And we have time for questions, please.
Please. So either everything was clear or everything absolutely not clear.
No, Armen Glebovich, sorry, there was a reduction of homotopy group to the class of homotopy maps of torus or vice versa. So
yes, this is very very nice result by Fox. Let me. Okay, I will show it.
So this is just you map torus to the sphere, and then you map a sphere as in construction of homotopy group or something.
Yeah,
like
that's
this.
true. That's true. If we consider the two-dimensional case, and we consider the maps of torus. So for torus, we should identify the opposite edges of the box. So we can do it in the following way. First, we identify only two of this, and we get some circle, or we identify the opposite two sides. Again, some circle. So we can describe the maps of the torus as two maps of the circle.
Sure.
This idea is the same, only it's a lot of combinatorics. You understand, there are lots of combinatorics because you can identify different size and so on. But the idea is very simple. But of course, the result is very nice. I like this result very much.
I see one hand from Professor Kravchenko. Please go ahead.
Sorry, I am not professor. I'm young mathematician.
Okay, good. You will be professor.
You will be professor. Yes.
In Krasnoyarsk, we try to investigate topological insulators with physicists who work in photonics, and we try to use the language of Wolfram cellular automata, and we have some results. And what we get? We get Wolfram cellular automata who modeling topological insulators, and we see that these cellular automata can be called linear. We can introduce the class of linear cellular automata. And my idea was that we can use the language of how you say involution space or C-star algebras and can you give advice? Is this study have some future and so on?
Okay, thank you for paying attention to this Wolfram cellular automata. Unfortunately, I don't know what is that, but I will have a stimulus to learn this. But let me say that there are several different mathematical approaches to topological insulators. Apart from this one, which I presented here, there is an approach based on K-theory, as I said, but not only on K-theory, also on C-star algebras, as you mentioned, but also based on non-commutative geometry, and so on. There are several different approaches. Some of them, of course, they are all equivalent, but some are more useful in some different situations. So that was one of the things which attracted me to this theory, because I like physical. First of all, I like physical theories, And secondly, I like when these theories have different mathematical formulations. But as I said, the main point is this wide energy forbidden zone or energy gap. This is the main fact. That's why we can apply topological methods. I'm not sure that I answered to your question, but that's what I can say on this topic. You know, of course, evidently much more about automata, cellular automata.
Maybe if these results are published elsewhere, you can share with references.
Yeah. If you can, in fact, we have written. I have written with my students a big paper, which already accepted for publication, and I can send it to you, which has, of course, much more facts. So
Okay,
if you
perfect.
write to my email is very simple: Sergeev, then this dog, and that's.
I believe it's very simple to find it. Okay.
Yeah.
Thank you.
Yes.
Okay, so more questions, please.
Oh, maybe I have another question.
Yes, please.
Does it still work for octonions? You speak about quaternionic case.
Yes. In fact, classification of topological insulators, which was done by Alexey Kitaev, is completely is given completely in terms of representations of Clifford algebras, so octonions in particular. So it's very, from a mathematical point of view, it's just the classification of representations of Clifford algebras. I haven't spoken about it, but it's completely mathematical. And in this paper, which I already mentioned, we give Alexey Kitaev construction.
Okay, good. So more questions, please. Well, we enjoyed very nice and clear talk, and since there are no more questions, let us thank speaker for a very nice talk.
Thank you very much. Thank you,
Thanks very much.
for attention.